chemical bonds. And we can measure electronic structure, which is important for optoelectronic devices. And the way such a system works, you insert a sample in the little chamber here, and there you pump down from atmosphere down to maybe 10 to the minus 6 millibars. And when you reach that pressure, you move into the so-called preparation chamber, where we can evaporate organic molecules or metals on top of the surface if you want to do some basically multi-layer samples under controlled vacuum, or doping, or metal contacting, whatever it is we want to explore. And when we're done in there, and now we're talking a pressure about 10 to the minus 9 to 10 to the minus 10 millibars, we move into the preparation chamber, that is, analysis chamber, that is connected to the analyzer, which is basically a bandpass filter to measure kinetic energy of the electrons coming out. And the trick is we have either an X-ray source or a helium source that provides photon of specific energy. Those photons are absorbed in material, emitting electrons. We measure the kinetic energy, and knowing the photon energy, we can then calculate the binding energy of the materials. So the lovely aluminum foil that you see everywhere, that is to reach the very low pressure of 10 to minus 10 millibars, one occasionally has to heat up the stainless steel chambers to get rid of water that's absorbed on the walls. And in order to ensure a very even temperature profile over the steel walls, we clad everything in aluminum foil, kind of like when you cook in the oven at home. So same trick. So that is the old beast, and this machine was actually designed for fast sample transfer, and also specifically for study organic materials that are radiation sensitive. So the light source, the UV light source, is coupled with a monochromator that gives us slightly better resolution, but also reduces a little bit the photon intensity, minimizing sample damage. So that is Moses, one of our machines. Then we have something slightly nicer, and I should warn you, this is a surface science lab, so it's always under construction, so lots of more mundane tools lying around. But here is the new beast. This is a commercial equipment. It's a Scienta, actually a Swedish company.
Yeah.
And this is a high resolution detection system. So the energy resolution is superior in this system. And we also use monochromatized aluminum K X-ray photons. We also have a better resolved energy source also for our photons. The design is the same. You introduce the samples over here, you pump them down from air down to again close to 10 to the minus 7 in this system. You move them into the preparation chamber, where we again can do various depositions of metal, organic materials. We can also mount a UV-vis transmission absorption system, so we can look at samples also under ultra-high vacuum. And when we have characterized and done our surface chemistry, we can then move them into the analysis chamber that has, again, this hemisphere that detects the electrons coming out with kinetic energy. So this is a better system in terms of energy resolution, but it's a slower system. So the sample transfer takes much longer time in this system. And also it's not as well set up for radiation sensitive samples as the other one. So these are two main pieces of photoelectron spectrometers. Then the lab also has a Glovebox system, a two-box system, where into the left side here, it's the wet box where we can do spin coating. And if we want to also electrochemical experiments, if we put in a potentiostats, there are feed-throughs for that. Then we have the central transfer system. And over here we have where we do electrical and optical characterizations. And we also have a PVD source, physical vapor deposition, with 3 sources for organic molecules and 2 sources for metals. And here we can do again thin film deposition under not vacuum, but under Glovebox atmosphere. So nitrogen in our case. So then we can, our final piece of useful equipment. It's this little thing here. It's a home-built Kelvin probe.
Nice.
Or actually part of it is home-built. And this enables the measure of contact potential, meaning work function of materials. And we can do it in ultra-high vacuum, in air, or under controlled atmosphere, so leaking in gases of certain pressures. And then see how the work function changes, which is interesting for some applications. So these are the main toys in the surface physics lab of the Laboratory of Organic Electronics. And actually the student over there, Shilun, is in the Wallenberg Wood Science project, so he's busy working away. And this is Chanye, who is the boss of the lab and our main expert on photoelectron spectroscopy. So with that, questions?
Yeah, do we have some questions? I mean, what type of samples would you usually put in this, these machines?
We generally look at organic samples, but metal, inorganic, anything works. They cannot be have too much liquid in them because it's vacuum. So if they have, of course, we will pump away the water, and that takes some time. So typically we'll pre-dry them before inserting them. So this is solid. We can look at powders, but we generally look at solid films. And it's important that the films are reasonably conducting. You can look at insulating materials, but then they must be very thin. And this has to do with that when you do the photoemission, you're constantly withdrawing electrons from the sample. So if you cannot balance those charges by basically electrons coming from the sample holder into the sample, you build up a positive potential that messes up the experiment. So insulating samples are a problem.
How thin?
It depends on how insulating they are. We have looked at Teflon, for instance, which is a very good insulator, but then the thickness of the films were less than 100 angstrom, so less than 10 nanometers.
Wow. Okay.
So it depends. If it's a conducting film, it can be very thick, but for insulating films, they need to be very thin. There is a trick you can do in the more fancy machine, the Sienta, where we have a so-called flood gun, and then you bombard the sample with a beam of low energy electrons to try to compensate for the electrons that we kick out. This enables, I would say, check of the elemental composition, but I personally do not trust chemical shifts because this electron beam and the sample charging is not uniform over the sample surface, so you get slightly different potentials and broadening of the peaks. Now I'm getting technical, but anyway, so it's you can look at insulating samples here, but it's more limited in what real information we can give you, or trustworthy information.
And what is the vacuum level?
Vacuum level, that is if you take an electron from a sample and you move it out from the sample so it's free but have zero kinetic energy. That defines the vacuum level. So I've taken the electron from the material, I have removed it, but it's just so it escaped. That is the definition.
Yeah, we have a question in the chat.
Yes, from Torbjörn Petersson. So Torbjörn is wondering, what is the lateral resolution for these measurements?
The lateral resolution is poor. They are not set up for that. So the Sienta, in theory, we can get lateral resolution, so maybe a couple of 100 micrometers, but we generally don't run it in that mode. There are better machines, so-called NANA-ESCA, that are set up for that, and then you can get resolutions down to micrometers. So, so I think if error resolution is needed, one does better to go to one of those machines. There are a couple in Sweden, and you have a PMIN Max Lab, for instance, that give excellent resolution. So,
what do you see as a potential for the wood-based applications? What kind of applications do you think you will get? The research questions.
I don't know. So we are now we're studying what we are doing, and that is using wood in either optoelectronic properties and also for we've done a little bit work with Xavier on the wood-based batteries or super caps. But yeah, so we hopefully a lot of people will be interested and contact us, and then sometimes we can say yes, we can help you, and otherwise we will say unfortunately no, this measurement is not for you, but maybe we can recommend something else. So so yeah, we are looking forward to see what is in store for us.
This is really great. But now the instruments are up and running, and basically we are ready to add them to the research infrastructure, right?
Yeah, so this center machine here, on Tuesday we will make the final calibration of the monochromator crystals. So we moved this equipment from Linköping to Norrköping. So now we can run with poor resolution, and hopefully by Wednesday next week we can run at high resolution. So that is the status. So
this is really fantastic. I'm very glad that we have now opportunity to expand the infrastructure and to add the XPS and the UPS characterization opportunities. Because I was getting a lot of questions from my colleagues from KTH. Yes, so please start formulating your research questions and preparing the proposals and send them to us to the infrastructure at Treesearch, and then Mats will evaluate it.
Great.
Thank you very much, Mats. Very nice presentation, very nice overview.